main change for that element of soil I've illustrated there is there's, from effectively zero shear stress, in this problem here, principal stresses are horizontal and vertical, but here we're developing shear stresses on the side of the elements. So we're actually creating a state of stress which we're shearing the soil in something that's called simple shear. So we've taken a sample, keeping the principal stresses constant, but increasing the shear stresses. Not quite true. I've said something slightly wrong there. What we're doing is taking a soil and we're leaving the vertical and horizontal stresses are remaining constant, but we're increasing the shear stresses. That's what I should have said. Now, clearly, that pile needs to be in equilibrium. And equilibrium is done in terms of forces, not stresses. So close to the pile, the shear stress pushing upwards on the pile must be high because it's summed over the area of the pile. But as we move out to this distance here, the shear stress is now summed over the area of the cylinder further away. So the area is getting bigger the further away you go. So the shear stress needs to get smaller the further away you go. So that always, every concentric cylinder is in equilibrium. This is why the shear strain decreases with radius, and it decreases quite quickly because the shear stress is decreasing with radius. And soil is non-linear in stress strain, so the shear strains drop off very quickly as you move away from the pile. The zone of disturbance around the pile is relatively modest. OK, so what do I want to say? We've said there's simple shear in the soil, and that results in an upward shear stress on the pile, as illustrated just there. If the pile were infinitely long, so we don't have a bottom and a top to it, then this is a very good description of what goes on around the shaft. It obviously breaks down slightly near the ends, and at the base here it breaks down slightly, but over a long pile it's a very good description. OK, next thing we need to look at is what's going on under the base of a pile. And here it's more difficult to see quite what I'm drawing, but that's the base of the pile there. Again, it's a cross-section. And what I've done is drawn a number of semicircles on that cross-section. But because it's a cross-section, they're not really semicircles. They're what are called hemispheres. So there's a cap on the end. So it's like having, effectively on the end of the pile, the first one is the size of a tennis ball, next one maybe the size of a football, and the last one the size of a beach ball. So we're thinking of hemispherical caps on the end of the pile, and we've cut through them, and that's what we're viewing there. When the pile displaces downwards, there's a very complicated zone of shearing right around the base of the pile, but once you get away from that, the soil is largely pushed backwards, and the mode of deformation is very similar to what you get if those hemispheres were increasing in size. So effectively, somebody has blown up the football and increased its pressure, and it's stretched outwards. So we're pressing in the centre, and it's causing each one of those hemispheres to increase slightly in size. And there's a mode of analysis called cavity expansion theory, which can be used to analyse that. So that's what's going on underneath the end of the pile. And this brings me probably to a really good place to draw this to a close. All I've put on there is obviously as the soil's been pushed away, this results in an increasing pressure on the end of the pile. So what we're saying is we've got an increasing shear stress on the shaft of the pile and an increasing pressure on the end of the pile. And it brings me to my point where I want to stop this lecture, which is to say this brings us to our pile capacity equation. We're saying that the capacity of a pile is made up of two components, base capacity plus shaft capacity. And the base capacity is just the pressure, which is called QB, pressure on the base, times the area of the base, And the shaft capacity is the shear stress on the shaft averaged over the length of the shaft, because it may vary with depth. So we have to average it with depth and multiply it by the area there. Next time, we're going to talk about how we calculate that end bearing pressure on a pile, and we'll talk about how we calculate the shear stress on the shaft of a pile. Okay, that's probably the best place to leave it. Piles get their capacity from two sources: shaft friction and end bearing. Okay, thanks for your attention. Yeah, of course you can. Just check it. You just hang on a sec. I just want to make a correction. Nobody said it at the time. It's going to be hard to see now. In this, let's see if I can actually focus it.